So in this circuit, whenever A, which is the lower 8 switches, is greater than B, which is the greater 8 switches, an output will assert is high, which I assign to LED 0. So you can see right now, both of these are 0, so it doesn't output. I'd also like to make a note that it is a signed value, so if you invert the sign, then that can affect it. So let's just say here, so now you can assign 1, 2, 4, 8 to A, and then B is 0. So then A is going to assert as greater than, and then that LED shows up. But then if you do 1, 2, 3, 4, 5, 6, 7, 8, if you make A negative, then B is greater, so greater than is set back to 0. And then you also can, compare two negative numbers. So let's say now B is greater, but now A is greater because B is negative. That'd be 1, 2, 4, 8, 16, 32, 64. Negative 64 versus like negative 8, right? But then if you make them both negative, A should still be greater. So 1, 2, 3, 4, 5, 6, 7, 8. So then you can see that A is still greater even as a negative number. And that will happen no matter what you put, unless it's the largest bit that is not assigned, since... Oh, wait, well... Oh, right, no, they're equal. That's why. Yep, pretty simple circuit. Not amazing to show on an FPGA, but shows the code works. So this circuit is a basic BCD incrementer where it will take a BCD input, which is 3 different hex values from 0 to the first 4 switches, the next 4, and the next 4. And then when I hit the center button, it will add 1 to them. So you can see if it's 0, 0, 0, you hit the button, it'll press 1. And then, if I press 1, it'll go to 2, 3, 4, and so on. And if I set this to 8, you can see it goes to 9. And then once at 9, instead of going up to A in hexadecimal, it will use BCD values and go to 10. And then you also can set it something similar where, if you have 99, it'll go back up to 100. Where basically, if it's at 9, it'll reset to 0 and increment the next value as 1. It has 3 of these incrementer modules in a row and then synthesized all to the 7-segment multiplexer. The next piece of code is an 8-bit barrel shifter that can shift either left or right. The first 8 switches are the input. The next following switch is the indicator to shift left or right, with right being the default if the switch is off. And then the next 3 switches are the amount that you're shifting between 0 to 7 bits. You can see here when I turn the switch on, that's just an indicator that the switch is on, and then this is the output LED. So here you can see that it hasn't shifted yet because these 3 switches are down. If I select 1, then it'll shift, since it's a barrel shifter, it'll shift over to the MSB here. And then if I shift by 2, it'll go again, 3, 4, 5, 7, and so on. Back to, the B7. And you turn all the way down, it's back in the original place. You can do this with multiple bits like this. You can see that it hasn't shifted still. And then you can, shift by 1, 2, 3, so on. But then you also can control which way it shifts. So then, let's keep this bit back on here. So nothing shifted yet. You shift by 1 over here. But then if you want to shift left instead, then it'll shift 1 bit left. You can see here, that's the original position, and it's shifting left now by however much you want. Pretty basic again, but you get the functionality on the LEDs to practice synthesizing it. All right, so this next piece of code is one of the first things I worked on. It is a 7-segment display multiplexer between each of the 4 7-segment displays. The way this works is that the segment output on the FPGA has 7 pins, and then there are 4 other pins to control the decimal points below them, and then there are 4 more pins to enable each separate display. So what you have to do is use a clock and multiplex through them pretty fast, so you can't see them changing, but so you can update them one at a time based on those hex inputs. It's pretty easy once you display it once, because then you can just recopy the code every time and just worry about the data going in and not about how it actually works. So the most significant 4 switches here are what turn them on, and you can see that those are controlled individually. The next 4 pins control the decimal points here, so you can see I can turn them on and off. This was code that was really useful to synthesize to the board just to get the actual visual of it to make sure it worked compared to synthesizing it. I also assigned the first 4 switches here to the hex values for segments 1 and 3. I wanted to make sure that they would both update at the same time. Pretty much what you're seeing right now. You know, you can set them all up to there to F, and then the next switches I assigned to segment 2 just to make sure that you could also update different values at the same time. I didn't have enough switches to assign something to segment 4 since I had the 4 control switches and then the 4 for the decimal points. So that's why these two are also the same, but you can also confirm functionality from this alone. For this piece of code, I created a stack, which means that it will hold a certain amount of inputs in memory, and the first input in will be the last one out. The first 4 switches here represent a hexadecimal input that is also represented here, and then this is the output. This LED at LED 4 represents if the stack is empty, and then LED 5 represents if the stack is full. So since you reset it here, you can see that it's empty. I was playing around with it a little bit before, so that's why I showed a 1 in memory before, but it is empty, so you can't read from it unless you wanted to with it being empty, but I don't know why you'd want to do that. So you can change the first 4 switches here and see the input change. I did add a clock divider so that I could press the buttons and it wouldn't automatically fill it very fast, so you see me hold it a little longer. So now you can see that I loaded the 3 in as the first input to the stack, and you can see that it now is not empty. I can pop it and read the stack, which basically just means it will move on to the previous input and go back down the stack. Now, since there's only 1 in here, it'll pop it and go back down to 1 because that's what was in the memory last. Never mind, it stayed at 3. That's probably because it was the last thing entered. But so you can also read now that it still is empty, so that you can't read this again. So if you write, you know, we can write a few. So we got 1, 2, 3. I forget what I set the amount to. Oh, some of the switches are getting stuck. Oh no, it's just 8. We don't want 8, we want 4. 5, 6, 7. I think I might have put like 8 in here. If not, I'll just start adding a bunch really quick. 9, 10 or A in hex, B or 11, C or 12. It's still going. Okay, I must have made this a lot larger than I thought. E, it might be 16, F. And then we're just gonna add a couple more. So now you can see that it is full. So then, you know, we can get rid of all these. We're not inputting anymore. If you try and input something else, you can't because it's full. But then if you pop it once, you can see it's not full anymore. So then you could put that input in. And then the top of the stack is what's outputting. So then you can hold this output. You can see that it is not empty or full, but we are popping all these numbers and then it will go back down to being empty. And that is a stack. So this code is a basic stopwatch with the first 4 switches being a duty cycle control for how bright the 7 segment display is. You can see when it's all the way off, you can't see it at all. And then it starts to get brighter as you go. So we'll just keep it fully on for now. But the next switch here controls if it increments or not. And then it counts every millisecond as a tick on the right. And then the next highest is seconds. And then this is the tenths place. So very similar to the code with the BCD incrementers before, but actually applying it to something like a stopwatch and using the IO on the FPGA. And you can clear it by pressing the clear button. And then what you can do is you can stop it, clear it, back down to 0. Pretty basic. So this circuit is an enhanced stopwatch. The first 4 switches are the duty cycle, same way, so kept that up. The next switch is go like before, but then the next switch is a control for which way you're counting. So if it's up, then you're counting up. If it's down, you're counting down. So right now you can see that we're stopped, and then we're incrementing, and then it'll actually count to 59 and then go up to a minute. And then you can also count down. Sorry, it's this switch. And then when it counts all the way down to 0, it'll go to the max amount, which is 959.9. Like I said, it counts every millisecond like before. And then you can see it goes back to 59. So in this video, I have a rotating banner, which consists of, let's see, what is it? 8 different numbers that were hex values that get shifted across either left or right on the 4 7-segment display. I do this with a 4-bit shifter circuit and then 2 switches to control if it should be moving or not, and then which direction. So you can see here, that's the enable pin, and then it'll start getting shifted in from the right out the left. You can see the hex numbers are 0 through 7, and then you also can reverse the direction. So this will be a way to display more numbers at the same time through 4 7-segment displays. So this circuit is a rotating square pattern that goes between 8 different states between the 4 7-segment LEDs. I made a different 7-segment multiplexer for this to handle the different states on when it would output. But pretty much what I use is just a counter that increments from 0 to 7 to basically determine what state the location of the square. And then you can control the direction of the square by either incrementing or decrementing that counter with the second switch here. So you can see if you enable it, it'll go counterclockwise. If it's disabled, it'll go clockwise. Something I had to do with this and the previous circuit was also have a clock divider and a counter so that the frequency of this would update slow enough to where you could see the different change, so that it was more of a frequency of like, 50 hertz or something like that. So this circuit here is a counter for a parking lot with another state machine. So how it works is you can think of it as this button here being towards the exit of the parking lot, and then this button here being towards kind of inside of the parking lot. So if you were entering the parking lot, you would go this way, and then you would increment the counter. If you were going out this way, then you would decrement the counter. So you can hit the buttons in a bunch of different ways, but the way that the state machine works is that if you are entering, then nothing is pressed, button A is pressed, both, B, then that, then you increment. And you can do this a couple times to say a couple cars come in, and then if a car leaves, you would go out this way. So this first, then both, then A, then none, and you can see it go down. And then, you can kind of go back, so you can like have the car go in the middle, back here, in the middle, and then out, and it'll still increment. So you just gotta think about all the different states that could happen for this counter. But yep, that's it. So this circuit is a basic dual edge detector. So it will assert an input for a given tick whenever a rising and falling edge is detected for an input. For this circuit, I have it connected to this button for the input, and then you'll see this LED assert for a tick, which is a second. I asserted the tick for that long so that you could visually see the LED. If you wanted to make this faster and so that the timing would be better for it, you could just have it work with the 100 megahertz clock and have a counter, but I did that for another part. So if you press and hold it, it'll blink once, and you let go, it'll blink again. It gets kind of weird when you press it on and off because you aren't able to hold it over one clock cycle because it has to be held for over 1 second for it to deassert like that. So it could be better implementation, but it's something to learn from, and I did improve it with the debounce counter. So this code features a debounce circuit where the 2 larger hexadecimal values on the left side of the 7-segment display is counting for the debounced inputs, and the right side is for the unfiltered inputs. So if I press these really fast, the idea is that you'll see that I guess it's a little off, but you can see that the unfiltered input will collect more than the filtered one, and this is because of the noise and the glitches that you get when you're pressing it. So you can see that it'll count more. It won't happen a ton, but it can help filter from inputs incorrectly happening. So this is the reaction timer circuit that I talked about for a good bit in my other video. It's controlled by 3 buttons here. The default idle state has high. You can reset it with the middle button. You start it by pressing this timer, and there's a counter in the background that happens that determines how long to wait, randomly between 2 to 15 seconds, and then you hit stop. This LED gets asserted basically when it's in the stimulus mode or the stimulus state, basically saying that you need to react to hit it in time. You can reset it by the mill button. If you hit it too early, it outputs 9999 saying you did it too early. And then, you can just keep going and try it. .302, not bad. So, like I said before, when it's inside of this state, there's actually a counter going from 2 to 15 on repeat, and then based on whenever you hit the start button, it'll determine how many seconds it actually waits, so that it's random and you can't just predict it. Circuit is a basic BCD to binary conversion, and it's used in the Fibonacci circuit that I'm going to show after this. Basically, these are the two BCD numbers that are controlled by these double set of 4 switches. So you can see, as I control this, the first 4 update, and then the next set updates those. So pretty much what I can do is there is a start procedure button here. We can convert, let's say 22, and then it'll convert it to binary under here. So you can see it's got 1, 2, 4, that's 6, 8, 16, and then 16 plus 6 is 22. So this can be used in a lot of ways, especially when interfacing with applications that you would want to read your output like this in the switches on a 7-segment display, and then turn it into binary to maybe shift the bits or manipulate them inside of a state machine. So this code is a basic Fibonacci module. So it actually takes 2 BCD values and then outputs them as 4 BCD values on the 7-segment display. So the first 4 switches represent the 0 number in the BCD value, and then the next 4 are the 1 number, or the tens place. So, you can go through here. If it's 0, this is just a start tick. This LED over here represents that it is in the idle state and it's ready to begin operation. It also outputs a done tick to LED 14, but since it's only for 1 tick on a 100 megahertz clock, you aren't able to see that with your eyes. But if you're using a logic analyzer or simulating this, it would be a good indicator on when to proceed in the test bench. But for this, you can represent, 0 is 0, 1 is 1, 2 is 0 plus 1, so you get 1, 3 is the previous 2, 1 plus 1, and so on. And so these first 4 represent the BCD value, so if you put something in more than 9, you're going to get some kind of funky. But, it can go up to 9. And then, you also can do let's say 30. So 39 would be larger. So if it's larger than, I think, 21 or 22, it'll output always greater than 9,999, which is what the 7-segment display is capable of displaying. So then pretty much I just have a case statement where during the state machine, if it's greater than that number, when it starts converting it to the Fibonacci sequence recursively, and decrementing that counter, then you will just output 9999 and be done. So you can save time on those clock cycles. So in this video, I have a basic UART module that is set to the parameters listed here. I have it connected to a COM port through USB on my computer and using PuTTY. It's set to a baud rate of 19,200, 8 data bits, 1 stop bit, no parity, and the flow control is X on, X off. So pretty much what I did is when I type in a ASCII character, it'll send those 2 hex values as a byte, and then it will, after reading it from the FIFO buffer, it'll transmit it back and increment that hex value by 1. So then you can pretty much kind of count up by the ASCII text by 1. So if you put in capital A, it'll return capital B. And it was just a good way to test the UART module worked, and then I got an application to work with the stopwatch. And also on the FPGA, in the next video, you'll see how I use switches to be able to control the stop bits, baud rate, error detection with some of the switches on here and make it a more fleshed out module. But so what I can do here is I also turned on echo for the terminal. So the keys that I would type into PuTTY, you'd be able to see them. So for example, if we type capital, oh, sorry, I got caps lock on. Type capital A, and then B, and then C, and then D. So you see that nothing is transmitted yet, but you can see that it does read the incoming ASCII text and then the outgoing one that it will send when I read from that buffer, which you can see that it increments by 1 on the counter. That's just some code on the synthesize module that I had. But then you can see when I read it, with a button on the board, you can see that that first one that I typed in, A, is now B, and then capital A is capital B, and then C, and then D, and then looks like the FIFO buffer was full, so we did not get that last E module. I think I have it set to 4 words, and you can see when I transmit now, even though it's empty, I think I had it so I could still transmit it, but it is reporting on this LED here that it's empty. It's just pulling whatever was written last to the FIFO buffer, which is something I've noticed in a lot of this stuff. But if you type something like 1, 2, 3, 4, 5, 6, 7, you can see how many I have again. It'll increment like 2, 3, 4, 5, 2, 3, 4, 5, and then it's back down. So yeah, and you could just increase the amount of addresses for the first in, first out buffer, depending on what you want that buffer range to be to make sure you get all your data. For something like this where I was just testing it, it was fine, but you'll see how that gets automated, and then I don't have to manually hit the button every time I want to read from the buffer in the future. So in this code, this is the fully realized UART module where I can control with switches 4 different baud rates, 3 different number of data bits, 3 different stop bits, and then whether you have no parity, even parity, or odd parity. And then this is something I also can set on PuTTY's end when I start the terminal. So for the baud rate, between 2 switches, you can select between 1200, 2400, 4800, or 9600. The data bits, you can select between 6, 7, and 8. The stop bits, you can select between 1 bit, 1.5 bits, or 2 bits, and so that just controls how many ticks you wait from the baud rate generator. Since we normally oversample with 16 ticks for 1 bit, you would just do 16, 24, or 32 respectively. And then for the parity, if it's 0, 0, it's no parity, 0, 1, even parity, 1, 0, odd parity. And then so the way that works for either the receiving or transmitting is pretty much it just counts the number of 1 data bits, and then if it's receiving whatever parity you agree on, it'll count those up and then compare to, if it's even parity, then if there's an even number of 1 data bits, it should be 0. But if it's an odd, then there should be an odd number of 1 data bits and 0. So that it can compare with what the parity is sent from PuTTY and then raise an error based on if it's receiving, if it's different. And then, yeah, so I guess I can just kind of manually change some of these settings here based on what we have. So based on last time, what we did is we just had this basic communication. So let's say this time we want 7 data bits, 2 stop bits, and then even parity. And then we'll make the baud rate, since we don't have 19200, we'll just do 2400. And then we'll keep that open. And then let's see here. So now we got to figure out what switches we had wired to these. So it looks like I had the baud rate to the first 2 switches on the right. So since that is 2400, it will be 0, 1. And then I just have the LEDs wired to the switches, so it's easier to tell what they are since it's kind of hard to see here. And then the data we had at 7, so it's going to also be 0, 1 on the next 2 switches. And then we also have the stop bits, which are the next 2 switches, which is 2. So then it's going to be 1, 0, a little different. Nope, sorry, that's the same. Gotta have one more over. And then for parity, we want even parity, which will be the next 2 switches, and 0, 1. It'll be like that. And then, this circuit, you can see here the 7-segment display is doing the same thing. It's the same counter circuit. I wanted to keep it the same just so, I'm working with something I know works, I'm confident in. I'm just slowly adding in these pieces of variability, just so it's easier to debug and test. And let's start here. I don't know if I had echo on or not. Looks not, but it's updating on the FPGA. You can see that as I'm typing, it is updated. And then if you read here, you can see what we got. So if you do 1, 2, 3, 4, then as you burn it, you get 2, 3, 4, 5. So same functionality here, but you are able, under the hood, this is able to have 2 stop bits, 7 data bits, and even parity. And then just for the sake of time, I'm not going to go through all of them, but you can get the gist of it and play around with the code more if you want. It is uploaded on my GitHub, but that's that. So in this module, I will be showing off the stopwatch circuit that is controlled through PuTTY and UART instead of on the buttons and switches on the FPGA. So I was really excited about doing this because I think it showed kind of how I was able to branch out into other I/O modules and start to connect a bunch of different pieces than just what's on the FPGA board for real-life applications that isn't just a timer on a development board. So what I did is I just configured the settings with that UART full module that I just showed, so it'd have 1200 baud rate, 8 data bits, 1 stop bit, and no parity, mostly just because I could use less switches on here. And so if I hit open, I also have echo on so you can see what I'm typing. So you can see here, after I type G, it is now incrementing. And then you also can type capital G. If I type P, then it'll pause. And then I can also type capital G to reset it. If I type U, it'll start counting the opposite direction, just like the enhanced stopwatch. And so this required making an interface circuit with some registers to basically latch the inputs for like the G, P, U, and then also the C for the clear input. Will set all of the values to 0, and it'll raise that clear input and set go to 0, and it'll reset the up down to counting up. And that's pretty much it. There is one more feature, so if I increment the time and then I type R, it'll actually send the time at any given point whenever I send it. And so this was interesting because I had to store the register values for the time of reading it. Otherwise, it would keep incrementing as it was transmitting these. And that was something I noticed in the test bench. Since it operates pretty fast, I don't think it would be too off, but it was more data I had to store, but you could probably play around with that to try and make it more efficient. It would also be a way, I could add like a new line. Well, so I added a new line, but I need it to like break back to the front. I was trying to make it easier to read, and then with echo on, it's a little harder to read, but that's something you easily could go back into. I figured it'd be worth my time more to get into some other stuff. But yeah, this kind of idea of applying inputs to UART in this general module of like this receiving interface and this transmit interface can be applied to a lot of things with different keys, basically to make either like a tick, like when I receive this here to send it once, or to latch it, like when I pause this, because you want that to hold with a register. But really fun stuff here. So in this code, I configured a standard PS2 receiving system to receive the scan codes from a basic keyboard. And so the way this works is when you hold down a button, so pretty much to preface this, I read the key code and then I send it through a receive unit and my UART module I designed. When you hold a code down, it repeatedly sends that key code, and then when you let go, a break code, which is the hexadecimal F0, is played, and then the make code, which is the key you press down, which I pressed down A, which would be 1C, was pressed. And so you can do this with all different types of keys. You can see you can tap it once, and then if you hold it for long enough, it'll repeat. So I wired this up first to see if I could receive the PS2 codes as their key codes, and then the next units, I converted them to ASCII so that you could read them as ASCII text on the UART for communication. So this is another PS2 keyboard model. So what I did is I used a state machine to process the make code after the break code is pressed and then convert it to ASCII text. So what happens is the state machine is in idle state until a break code or F0 is pressed, and then it'll read the following make code, which you can tell what key is being pressed. And then after that, you can convert it from a table or like just a case statement to convert it from the key code to the ASCII text. So then when you type a key like A, it'll return A. And then you can do this for a bunch of things and just write a bunch of stuff. And so you aren't getting those 2 hexadecimal values because it's converting it to ASCII text. Before, you did have to go the 2 key code values to the ASCII text of their respective like letters or numbers. So you had to do the conversion for the hexadecimal values, but this, it's ASCII text, but then it shows up in PuTTY. So, this would be a way where you could write messages to PuTTY to control things on the computer, and then vice versa, you'll see how I can do this a couple different ways. So, yeah. So this next piece of code was similar to pretty much, instead of transmitting the keys when you would hold them down, or whenever you would release them, it'll transmit the keys when you hold them down. So pretty much right when I start pressing a key and then I hold it, it'll get released. Whenever I let go and it scans that break code, it will stop transmitting because it'll read F0. So you can do this, and you can still, if you type fast enough, you actually can still use it. So I'd say this is just an ultimately better use case, I guess, if you're trying to like use more. But also there's some times where you would just want to let go if you just want like one tick of something, but you also could handle that on the Verilog side if you still want this functionality. So this next piece of code covers a shift module where pretty much there's two different case branches for the ASCII conversion, and a state will handle if you're holding down shift or not. So now if I just type A, B, C, it'll come down as lowercase, but if I hold shift, like I am right down here, then it'll be capitalized. So one thing with this is it's a little slow. Like sometimes if you type too fast, there's just a little bit of a lag. So I don't know if there's maybe a way to speed up the state machine or the processing with the shift case inside of it. But it has the functionality. It makes it so you can have different functions for if a command is shifted or not. So like a lowercase a and a capital A could mean something else when you're controlling your unit as it's getting received or transmitted. But yeah, that's about that. All right, for the last video, I am using the enhanced stopwatch that I used before and then also in the UART modules, and I'm just using it with a PS2 keyboard this time. I didn't have that hooked up to the UART with the receive function, I just controlled it from here, but you can press G and it'll go. You can press P and it'll pause. You can go again, you can reverse the direction, and you can clear to reset it. So same exact functionality, but it's connected directly to the FPGA board and not through the UART COM terminal. So kind of flexible, I guess, if you don't want to use PuTTY for something and you just kind of want to have it as its own piece of hardware.